I've seen children starting in the beginning, things are going very rosy, nice, logical approach, physical chemistry is very nice. As soon as organic chemistry begins, they start panicking. And that's why children from all these so-called institutions, they come back to me and I have to every time make some batches separate for them. Because in their school, some different speed is going on and they're stuck and facing difficulty in the same mechanism part and all that. Preparation is very short here. Physical properties, and then we jump on to the chemical properties where chemical reactions will come. Physical properties, two very major ones. First, they are relatively non-polar with respect to other alcohols or alkyl halides and all that. They are relatively non-polar and almost insoluble, nearly insoluble in water. But they are soluble in the polar solvents. Yes, polar solvents like any alkenes or alkanes, hexane, it will be soluble. Yes, quite soluble in most of the organic solvents, acetone, ether, methylene, chloride, chloroform. Yes, alcohols, it is soluble. Another property, acetylene or propine, that means ethine or propine or butane, they are all gaseous at room temperature. Yes, same way as alkanes and alkenes are, correct? And another thing, that their boiling points are almost equal to that of the alkanes or alkenes if we are comparing them having same number of carbon atoms. Yes, that means ethine, ethene and ethane will have almost comparable boiling points. Make sense? Yes, almost nearly same. Good. Now we jump on to the chemical properties. Some of the basic things which you should know. First, there is presence of pi bond in the ethine. So obviously chances of attack will be there. Yes, when that happens, who will attack at the double bonds, at the pi bonds? Who will attack? Electrophile. Good. So electrophilic addition chances are there. Everybody agrees? Second thing, they have a hydrogen which is connected to a sp hybridized carbon. Sp hybridized carbon. This is very important point. I want one of you to read. Risha, read this.
Presence of acidic hydrogen atom. The hydrogen atom attached to the triple bonded carbon can be easily removed by a strong base, and hence acetylene and 1-alkynes are considered as weak acids.
Very important here. Did you understand this part? The hydrogen atom which is actually connected to this triply bonded carbon, they can be easily removed by any base, any strong base. Correct? That's why this ethine, you call it, or any one alkyne, they are usually weak acids because their H plus can be removed easily. Correct? Now, why that happens, let's hear the explanation. Read that.
Since s electrons are closer to the nucleus than the p electrons, the electrons present in a bond having more s character will be more closer to the nucleus. Due to high s character of the CH bond in alkyne, s equals to 50%, the electrons constituting this bond are more strongly held by the carbon nucleus. With the result, the H present on CH can be easily removed as a proton.
Is this clear? Makes quite sense, na? Yes, s electrons are more closer to the nucleus than the p electrons. Yes, and electrons are present in a bond, and the electrons which are present in a bond and have greater s character, that means they are more closer to the nucleus. And because of that, what will happen? That CH bond in the alkyne, the electrons which are constituting that bond will be more strongly held by the carbon nucleus. Because the more closer you are to the nucleus, the greater the nuclear pull you are experiencing. Yes or no? The more closer you are to the nucleus, the greater the nuclear pull you are experiencing. The more pull will be there. That means H plus which is present on the CH, they can be easily removed. Nice. Here higher sp character, so more pull on the electrons of the hydrogen, so H plus can be easily removed. Here comparatively less pull, here least pull. Understood? So this is most acidic, then little less acidic, and least acidic. All good? Acidic nature reduces this way. I hope it is clear. So relatively, and if you compare them with respect to other acidic fellows, like water has the highest. After that, alcohol. Then comes alkynes. Then basic fellows begin here. This amine. In amine also H plus can be removed. Yes, correct. Then there is double bond alkene. Then there is alkane. This is very important. So you can remember this order. But again, connect it with logic every time. H plus can be easily removed here. So it is more acidic than alcohol. Then comes alkyne. Then comes amine or ammonia. And then comes, this is kind of basic only. Alkenes is even less than that. So more basic. Alkane is even more basic. Good? Good. Understood, everybody? Okay. So electrophilic addition, which is possible. Now, if we talk about reactivity, keep that in mind. Even though alkynes have 2 pi bonds, but still the reactivity order wise, alkenes will be more prone to electrophilic addition than alkynes, and obviously alkenes cannot. So this is the reactivity order. Is this clear? Can alkanes undergo electrophilic addition or free radical addition? They cannot undergo electrophilic. Yes, only free radicals can break the bonds and all. Moreover, free radical substitution happens. Understood? Remember? Good? Okay. Fine. So, so one reason why this happens is kind of given here. What is that? Whenever you kind of addition reaction, usually you initiate it with the help of electrophiles, which are positively charged, which are looking for more electrons. Yes, and in this case of electrophilic additions, what happens? The reactivity of alkynes towards electrophilic additions is usually lesser. Yes, correct. Because once the substitution happens, the hydrogen will be removed. The acidic hydrogen will be removed, and it is most acidic. That's why. So the pi electrons are kind of very tightly held by the carbon nuclei, and that's why they are not very easily available. Where there are, why? In case of alkynes we are talking about. Yes, they're not just 2 pi electrons, there are 4 pi electrons. Yes, if you remove the first ones, the inner ones usually are more tightly held, not easily given. That's why they have less reactivity, less prone to electrophilic addition than alkenes. Another reason is, what do they form? I told you always, whenever you have to see any reaction, check final or the intermediate product. If that is stable, reaction is more reactive. Reactant is more reactive. Make sense? Yes. So if you do the hydrogenation, do the electrophilic addition, and H plus is the most common electrophile, once that gets added, this is what is your intermediate or the carbocation which forms. Yes or no? Now you compare this and this, which is more stable. A doubly bonded carbon having positively charged or a singly bonded carbon having positive. That means heavy electron cloud and lack of electron. Or this. This is a destabilizing factor. Yes or no? A doubly bonded, that means heavy electron cloud, and over that there is positive charge. Yes or no? Destabilizing factor. Make sense? That's why this is not that stable. And if the intermediates are not that stable, that means this fellow will be less reactive. Good. Alkynes will be less reactive. Stability of intermediates is given here. Positive charge on more electronegative atom is less stable. Hence, this fellow is more stable. Good. I hope you understood why it is more electronegative, because it is able to pull electrons more strongly. Why it is able to pull electrons more strongly? Because sp hybridized carbon. Nice. Makes sense? Correct? Greater S character. Just say that. Not sp hybridized. After positive charge comes, it is sp2 hybridized. But yeah, I think still it is sp hybridized only. Yeah, 1 and 2. Yeah, still sp hybridized. Basically, greater S character means more closer to nucleus. That means more pull. That is more electronegative. If somebody is pulling electrons, that means they are more electronegative. Yes or no? Good? Yes. Next thing, hydrogenation. For hydrogenation, we can go via our simple same process to use catalysts like nickel or platinum or palladium. Correct? Do that same way with even alkynes also. Correct? If you do not stop the process, or the availability of hydrogen as well as catalyst. The reaction will keep on going and the final product you will get will be alkane. But systematically it will happen. Yes? Makes sense? Is this clear? Yeah. Another beautiful thing is if you use Lindlar's catalyst, that is palladium with calcium carbonate and quinoline or Ni2B, remember nickel boride? NiCKEL, not KLE. Okay. So if we use nickel boride or the Lindlar's catalyst, then the product which comes, they get added in the cis way. We have already seen the mechanism of this in the last chapter. Remember? Cis addition. And when we saw Birch reduction, we found trans addition. Remember? In case of Birch addition, what was happening? Trans addition. In case of cis addition, what was happening? In case of Lindlar's catalyst, cis addition. These two are very important. We have seen it already. Yes or no? With all mechanism in the last chapter. Please go through that. Good. Now comes the so what are the difference in the catalyst? Here we use Lindlar's catalyst or nickel boride. Here we use sodium with liquid ammonia. Obviously hydrogen is being added, so hydrogenation is happening. Good. Okay. Addition of halogens. Again, same, by the way, I hope you remember the mechanism. Same electrophilic addition. Yes or no? Same electrophilic addition. I hope you remember. Good. Now addition of halogens, halogenation, that is also electrophilic addition. The reactivity order also you know. Cl2 will be highest, then Br2, then I2. Why is that happening? Because already there is heavy electron cloud and all these pi bonds have to be substituted with chlorine. Now you tell me who will have greater, who will, if you put 4 iodines here, iodine is huge. Yes or no? If the product is not that stable, why will this fellow be reactive? Why will HCl or HBr or all that will be more reactive? Sorry, Cl2, Br2 or I2 will be more reactive. Yes, understood. So if 4 iodines are present, that is not that stable. That's why I2 has least reactivity. It's the other way around if you check for Hi or HBr or HF. I hope you remember. Good. There the reactivity reverses. Good. Everybody understood? Let's move on. So mechanism again simple. You use Cl2 and FeCl3. FeCl3 is our what? Electrophile producing agent. It helps you in producing your electrophile. How? This FeCl3 will help you here also. You will see this fellow in the aromatic compound reactions also. He helps there also. Yes? So how does it help? It basically takes away one of the Cl plus Cl minus, thereby producing Cl plus. And this is our electrophile. Now that electrophile comes close to the triple bond and it joins there. Good? Yes? All good? This is a less stable incomplete octet, positive charge on the carbon atom. So for that what happens? Temporarily you will have this type of bond formation, chlorine with both the carbons. This is more stable because octet gets complete. Yes? But obviously positive charge on the chlorine atom. It is a cyclic cation in one sense. Then once again FeCl4 minus will comes from that. Who will come? Cl minus will attack on from the other side and it will join. Trans addition. All good? Bring another one. Again this double bond also will go away. You will have 4 of them connected. Nice. Same procedure repeats. Is this nice? Did you understand? Yeah. Okay. So acetylene tetrachloride is also called as Vestron. Remember that. It is also called as Vestron. And when you treat it with calcium hydroxide, it will form Vestrosol. It will form Vestrosol. What happens there? The H plus and the Cl minus from the neighboring carbons, they leave. Dehydrochlorination. That means elimination happens here. Yes or no? Elimination of HCl. Dehydrochlorination. Yes. Happens here. Vestrosol is produced. Or tricline. It's also called as tricline. Yes. Why these type of names? because they are used in the textile industries. They're used in the textile industries as solvents. That's why this type of name. Okay. Yes, reaction with Br2, similar ways, you will have dibromo. Yes, if you use water. Correct? With either dilute bromine or with bromine water. So this one is bromine water, this one is dilute bromine. With bromine water, dibromo alkene is formed. With bromine liquid, that means more concentrated bromine, you will have tetrabromo alkene formation. Good. I hope it is clear. Obviously, where do you have greater concentration of bromine? In bromine water or in bromine liquid? Obviously, bromine liquid. Yes or no? Yes or no, guys? Yes? The same way electrophilic addition one by one happens, as we have seen in all these above cases. Same way. Understood? In all these cases, as we have seen. Good. One Br plus will join first, and then next Br minus will attack from the other side, like that. Reaction with iodine, you use iodine with ethanol, you will have alkene formation. Addition is happening. Then use with ammonia, which is a weak base. Only two iodines will join, but this time hydrogen gets replaced, forming ammonium iodide. Good. So you will have no hydrogens, diiodoacetylene. In this case, addition happens. In case of ethanol, always remember alcoholic. If you are using alcoholic KOH or alcoholic iodine and all that, it will lead to the addition. Yes? Make sense? But if you're going for something like anything with ammonia, a base, then that leads to substitution. Good? Write it down somewhere. That's important. So this is how reaction with alcoholic I2. And why does substitution happen? Very logical. Ammonia will connect with one of the iodine and form ammonium iodide. Now obviously, if ammonia is taking away one of the iodide, what remains? One of the iodines remains. And if you have sufficient number of such iodide ions, they will attack. In this case, where addition happens, what do we have? I plus getting added. Yes or no? Ethanol, usually what it does, it takes away one of the I minus. I plus remains, which is our electrophile, so electrophilic addition happens. Nice? Good. But in this case, what will happen? NH3 plus combines with NH3 combines with one of the I plus. I minus remains in this plus. Now what will this I minus do? They will give their electron, and because this carbon is more electronegative, it will give their electron H plus value, and iodine will join. Here also H plus will leave, again iodine will join. That's why substitution. Both the hydrogen gets substituted by iodine. Clear? All of it depends on which is the reacting reagent here. Here it is the electrophile. Here it is the nucleophile. Nucleophile causes substitution, correct? And here electrophile causes addition. I hope it is clear. Understood? Yes? Fine. Addition of halogen acids, HX, obviously follows Markovnikov's rule. I already talked about this some time back. Remember? HI will be most reactive than HBr, HCl, HF. Fine. Do with that, you will get geminal dihalides as the major products. Mechanism, let's see that. First step, H plus will be your electrophile, will join, then this is your intermediate. Next step, X minus comes and that joins. Correct? Once again, if you bring H plus, one more H plus and will happen, then you bring X minus, then what will happen? Another thing, here this fellow is more stable. Why? Because X minus will have some plus M effect, mesomeric effect. Good? Correct? Yes? Everybody understood? So that X, that halide ion will have, halide connected to that will have plus M effect. On the other hand, in this case, Since it is on the same carbon, this is connected on the different carbon, we have inductive effect coming into picture. Make sense? It will be pulling all the more electron, all the more making it positive charge. Now the question arises here, why it is not happening? Because positive charge is on the same carbon to which halide ion is connected. So he can obviously give his lone pair to take care of this. And because he has excess lone pair. Yes or no? Rather here, he pulls. Because no immediate positive charge on the same carbon. Good. So here plus M effect, here minus I effect, obviously making this fellow more stable. Are we good? More stable, less prone to reactivity. Here it is more reactive, less stable. Easily a nucleophile can attack on this carbon. Yes. Obviously, if this fellow participates, then X minus will form geminal dihalide, which will be the major product because the intermediate is more stable. Correct? But in this case, what will be the minor product? Vicinal dihalide. X minus will attach on the different carbon. I hope you understood. Yes, geminal dihalide is the major product because this is a more stable intermediate. Ask me doubts, guys. Are you able to understand? Sure? Minu? Sangvi? Risha?
Yes, sir.
So the vicinal dihalide part once more you tell, please.
Okay. This will form, this is clear. This fellow is only written here and this is more stable. Because this is more stable, geminal dihalide will form. That means X minus comes from the other side. Correct? And he will attack here. So on the same carbon, XX is connected. Good. But if this fellow participates, X minus will come from the other side. What is it? Vicinal dihalide. Here X is connected now on the neighboring carbons. That is called vicinal dihalide. This is on the same carbon, so geminal dihalide. Simple. Similar way, do you remember we also saw, apart from addition of hydrogenation or halogenation or hydrohalogenation, we also saw addition of hypohalous acids. Remember? Hypohalous acids. We also saw that. HOX, HOCl, HOBr, HOI, all that. Yes? Exactly same way it happens here also. Only thing is, when chlorine is connected, to make it more stable, a cyclic cation forms. Then the hydroxide ion will attack from the other side. Yes? I hope it is clear. How do they break? When you say HOX, this breaks down into OH minus and X plus. Is this clear? Oxygen is more electronegative, na? Yes or no? Oxygen more electronegative, so obviously minus compared to halides. Obviously, if you have fluorine present there, then it's gone. That's why in comparison, we are not taking fluorine. Do you see? We are checking only chlorine, bromine, iodine, those who have lesser electronegativity compared to oxygen. So then it is OH minus X plus. Good. This is our electrophile. Now this electrophile will attack first, will join, form cyclic cation. Then this fellow nucleophile in the next step will come from the other side and will join. Good. Yes. Again follow the same whole procedure. Even this double bond will be gone. You will have singly bonded fellow. Now there also, if you have to see, if the double bond, if the positive charge comes on that carbon, correct, you have to see which is more stable. Yes or no? Correct? You have to see which one is more stable. So in this case, as the positive charge came where OH is there, correct, this is chances of formations. That means Cl minus can either connect on this carbon or it can connect on this carbon. So if it connects on this carbon, that means then positive charge will be here. If it connects on the other carbon, correct, then positive charge will be here. Fine. Which is more stable? Think again. In this case, plus some effect, plus R effect. In this case, plus M effect, you can say. Even this chlorine also has a lone pair which it can give, but who is more likely to give? Oxygen is more likely to give. So plus M effect of OH group is greater than plus M effect of chlorine. Good? Yes? Okay. That's why this is more stable. And then in the next step, if you bring OH minus, obviously this is more stable, so this will connect here. If in this case, it will connect here. Yes? Is this clear? The only thing is, even though this fellow was more stable, listen to me, this is very clear, this is very important. Even though this fellow was more stable intermediate, the product form must have been much more stable. No. Because if two OH fellows are connected to the same carbon, quickly they will leave as water. H plus OH minus, water leaves. Dehydration will happen. So anytime, remember, if on the same carbon you have OH group connected, yes, water will leave. Make sense? And double bond O will form. That means what do we have now? Ketone. Dichloroketone. Nice. Yes. So the less stable, what do you call? Less stable intermediate will give us a more stable product this time. That because OH will get connected here. Now the OH is not on same carbon. Can you see that? Are they on the same carbon? No. Is this clear? Is this clear? How you get this product as well as this product? Nice. Okay. HOCl. Okay, hydroboration, we already saw that in the presence of THF, tetrahydrofuran. Yes or no? Exactly same thing. First, try alkyl, in this case, alkali. In this case, there is an alkene that will be connected to boron, which is electron deficient, correct? And then basically BH3 is not so stable as monomer, and that's why THF is being used, correct, for its stability. Then one by one, as this comes close by, one by one each and every bond will break, one H plus will leave, and they will keep on connecting. So this is first one which got connected. Did you see? Yes, first one which got connected. Then same way, if another one you bring, second one gets connected, and bring another alkyl group, third one will get connected. Each hydrogen will keep on leaving one by one. At the end you have this exact same thing we saw there. Only difference was, in case of alkene, this double bond was not there, single bond was present. Yes, good. Okay, now basic oxidation, if you do use hydrogen peroxide with the base, you will have enol formation with BOH whole thrice, which later on can also turn into keto formation. Enol and keto, do you remember? What are they? Keto and enol. Where did you hear this? Come on, isomerism.
Tautomers.
Tautomers. Ketoenol tautomerism. Yes. So this is an enol formation. This is keto formation, which happens. Yes. En all. Correct. And this is keto.